A very warm welcome to everyone. Welcome to the course of Remote Sensing and GIS.
Targets we have seen, and individually we have dealt with them, and together in a single spectral response curve we were trying to understand. So that was the last part whatever we were discussing. So a kind of summary: leaf actually, if the all the four wavelengths, which is nothing but your red, blue, green and your infrared, if it is falling onto your leaf which is having a high chlorophyll content, what happens? Which wavelengths are getting absorbed? Your blue is getting absorbed and your red wavelength get absorbed, and it reflects back all the green and infrared. So that's the behavior of your leaf. Next, coming on to your water, what is happening? Just a reverse of that. The shorter actually comes out reflected and the longer wavelengths get absorbed. Your infrared radiation and your the blue red actually gets absorbed, and your blue and green actually comes out reflected back. That's the behavior of your water. Next to that, we have seen soil behavior, right? Soil actually, it's not a single parameter dealt target, so that's the reason you have some influencing factors. Your soil moisture influences your reflection pattern. Your soil texture actually influences your reflection pattern. So that's the reason if there is some presence of moisture, you will see the reflection percentage gets decreased. And moreover, we have understood that the behavior, if you see how the reflection pattern actually varies is, from the red, blue, green and infrared, the reflection pattern actually is high only. Right? A little absorption happens, but what is happening is, if the moisture content is high, the reflection percentage actually gets decreased. Okay, so the other curves also we were seeing. Next to that, soil texture. So how fine is your soil, how coarse is your soil also controls the reflection pattern, because the other day we were talking about the types of reflection. One is a diffuse reflection, one is a specular reflection. So the type of reflection, which type comes into picture also is controlled by the surface pattern. How rough is your surface, how smooth is your surface, right? So very fine grain, obviously you will have a kind of smoothness coming into picture. But when the coarse kind of soil is coming into picture, what is happening? The roughness is increased. So again, your reflection pattern changes. So we have seen that in the soil, generally you will have a gradually increasing pattern of your reflection pattern, but at some parts of your infrared radiation, starting from 1.4 micrometer, 1.9 micrometer, 2.1 micrometer, at some parts of absorption, those are called as water absorption bands. At those wavelengths, you can see that the absorption, a small decrease in the curve will happen, where exactly the reflection pattern takes a change. High absorption happens at those points because of the presence of water. Right, so that's the behavior of soil we have seen. So yesterday's last part was all these targets are sitting in a single spectral response curve, and at the same time, if I just overlap or overlay your satellite information onto that, I'm trying to understand which bands are important to me, or what are the bands, what is the spectral information of that. Okay, so let's go on to the PPT and understand what is the kind of how actually your spectral response curve is overlaid with the satellite information. Okay, so this was the last this was the last slide whatever we were seeing, right? So you can see here how many targets are sitting here. There are 5 targets actually. You can see turbid water is there, clear water is there, wet soil, dry soil and vegetation. So approximately total 5 targets are sitting here. So first, initially, if you concentrate on the clear water, what is happening? Water, we understood the behavior. You can see a small peak coming around your, kind of blue has come into picture, blue and green. You're able to see. Next, when turbid water has come, you can see you are seeing a green there, and next to that you can see a small peaks coming into picture, right? So that's your turbid water. Next, if you see the vegetation, just now we understood that a small curve or a small kind of peak we will see by green, and next to that a high peak has come into concentration, come into picture, which is from your infrared radiation, right? So now if someone wants to differentiate between your water, clear water and your vegetation, clearly you can see here in this part, there is a drop by clear water and there is a peak by your vegetation. So clearly, if I pick the information of my fourth band, okay, number 4 you can refer here. This is the Landsat thematic mapper bands, which is having a fourth band. Fourth band is nothing but fourth range of wavelength. So fourth band has some wavelength ranges. We will be seeing in the today's class what is that wavelengths or all. Okay. So fourth band, if I simply concentrate and see, one target is showing me a reflection, high reflection, and one body is showing me a zero reflection. So now when I refer to that fourth band image, yesterday I was showing you the satellite image which has white color in that, black color in that, right? So black is nothing but zero reflection, white is nothing but 100% reflection. So now if I refer that figure and see, all black patches which are there are nothing but my water, and all white patches, whatever I'm trying to see, is nothing but my vegetation. So that's how actually we interpret from the satellite image, because I'm not going to the site or I'm not going to the field or ground to check really what is that. I'm sitting at my station laptop, right? At my place itself, I'm seeing that satellite image and trying to interpret what is the object which is sitting there. And which wavelength I'm dealing is also really important. If I simply pick up my first band, which is your mix of blue and some part of green is coming, if I wanted to differentiate between water and vegetation in this area, I cannot differentiate because both of them show a similar pattern of reflection. Which band I need to choose is a challenging factor here. Because if I choose band 1 and try to differentiate between water and vegetation, both of them more or less show the similar kind of reflection. But if I pick for band 4, then I will be able to differentiate between your the clear water and your vegetation, right? So I should know first initially what is the spectral response of each body. Then only I will be able to choose which band to be seen for interpretation, right? If I don't know which wavelength responds to which body, then I cannot choose it, or I cannot rather interpret what is that image showing me, right? So that's the reason spectral response is very, very important to us. Next, if you see dry soil and wet soil, what is happening? Both of them are showing a kind of similar pattern. If you see a gradual increase in the curve has been observed, a small drop is seen exactly at 1.4 and again at 1.9 and again at 2.1. These are nothing but the water absorption bands, okay? And you can see a large variation between this orange curve and brown curve. What is this showing us? It's showing that the moisture content, due to the presence of moisture content, again between the dry and the wet soil, there is a difference in reflection pattern. So kind of curve, if you observe there, the shape is more or less, the trend is more or less the same. But what is that? The reflection value is little changed. You see the percentage, almost it's somewhere between 50%, and here it is only at 20 to 30%. So the reflection value or the percentage of reflection actually has some change in the number. But the trend or the pattern, what it exactly follows is more or less the same kind of pattern. Okay. So now these are the targets and we are trying to overlay which band is what and in which band I need to concentrate, right? If simply you wanted to study about soil, you can pick about these bands. These two bands, if you just see about the 5 and 7 band. So if you try to understand these two bands, you will understand the pattern of which type of soil or what is that type of soil, right? So that's what we will move on to the next. So now if you remember where exactly we are in the flow chart, we started with our source of energy, traveling all through the atmosphere, understanding so many phenomena of scattering, absorption, and after that interaction with the target. Now the reflection has happened. The spectral response is being coming out from the target. Now what my satellite should do, it should capture this reflectance, transfer that or convert that into a readable format. So my satellite should capture this information of reflectance. So what is that satellite? How many satellites are there? Or what is that satellite? How it's going to revolve? What is that all concept we are going to understand today? Okay. So the next part of discussion is that we are at D. Okay, satellite. So let's see what are these satellites, what is this orbits, right? So let's see this curve first and then we'll move on to the satellite part. Okay. So this, if you see there are so many curves here. Okay. So you can see what are these curves. These curves are nothing but, you can see first curve is nothing but your clear water. You can see the clear water, what it is doing. It is just showing a peak at this part. which is nothing but your green, that shade actually, not green exactly, next to the violet blue, 0.45 to 0.5 approximately it is showing a peak. Next, what has happened? Your turbid water has come into picture. Turbid water, when we say it may be due to the presence of sediment, it may be due to the presence of pollutants or algae, something. What has happened? A peak has just taken a small shift where exactly your green is more dominating than blue. Okay, next to that, it's your dry soil. Where is that dry soil? This is your dry soil, this pattern. You can see the soil always has an increasing trend of the pattern, the reflection pattern you can see. When you will see a decrease at your infrared region at 1.4, it starts the decrease. Okay. Next to that, you have the vegetation. A broadleaf vegetation is there, a stressed vegetation. Where is the difference? This is the broadleaf vegetation. You can see this curve. Similar, we have seen exactly at the reflection pattern has just increased at your 0.7 approximately, where your infrared actually gets starts. Okay, next to that, we see the kind of stressed vegetation. The same pattern is here actually. So the reflection pattern here, what has happened? The stressed vegetation is nothing but the kind of healthy vegetation. If you see, in the autumn season or so, if you see, the chlorophyll content will be very less. So the reflection pattern here actually is little low. Why? Because your red, blue, green actually mixed together and they show a similar pattern of reflection. So that's the reason we see the yellow color. Okay. Next coming, this is the fresh snow. So you all know why this is having a highest peak in this reflectance, because we know snow is nothing but a white body. Whenever the radiation falls, obviously you see a high reflection. No absorption happens there. A high reflection comes into picture, and high reflection also, all the visible wavelengths almost they show a similar pattern, kind of all are at the similar peak. So that's the reason we see it as white color. Okay, so this about this reflection patterns. Okay, next, the kind of satellites. So how many satellite orbits are there? Okay, we will understand first what is this orbit, how many satellite orbits are there. Okay, and next to that, we will understand what are the kinds of important satellites we are going to see. Okay, and what are an Indian satellites, what are the characteristic features, all these things step by step we will be learning from today's class. Okay, so today's class is your satellite orbit. So now you can see the picture which is seen here, right, on the right hand side, where exactly we are trying to see two orbits are there. So this is our Earth's surface, and you can see that it's rotating like this. We know that it rotates around the sun, and about its own axis also it moves on, right? So now there are two types of orbits which are there here, which is called as, one is called as geostationary and the other one is called as geosynchronous. Okay, so now talking about the satellite orbits. So now whatever the satellite will launch into the space, we have three kinds of orbits here. Okay, one is called as geosynchronous orbit. The second one is called as polar synchronous or sun synchronous, and the third one is called as geostationary, which is a kind of sub part of geosynchronous. Okay, so strictly talking, there are only two orbits. Okay, a special case of geosynchronous is geostationary. Okay, so what are these two is, one is Earth synchronous, the other one is sun synchronous. Earth synchronous is nothing but, we know that the kind of orbital period of our Earth is nothing but approximately 24 hours, we say, right? So it's nothing but 23 hours, 56 minutes and 4 seconds, right? So 24 hours. So within that orbital period, if your satellite is synchronized, it is called as geosynchronous. So the time period of the Earth, if you are just sinking your satellite to rotate around its own, or rotate around the Earth's surface, at the time scale or time period of the Earth's rotation, it is called as geosynchronous. Okay, so you are synchronizing your orbital or orbit time with respect to the Earth's rotation. You call it as geosynchronous. Okay, what is sun synchronous? Sun synchronous is nothing but if you synchronize your rotation of the orbit or rotation of the satellite with respect to the sun's rotation. Okay, That is called as sun synchronous. So with respect to which planet are you synchronizing? Is it with Earth or is it with Sun? If you make it with Sun, it is called as sun synchronous. If it is with Earth, you call it as Earth synchronous or geosynchronous. Geo is nothing but Earth. Okay. What is this geostationary? Geostationary is nothing but it is also tuned or synchronized to the Earth's rotation only. But what is it's happening is it only concentrates at your equator part. Okay, so here the rotation is not happening at an angle. Okay, or I'll show you one clear picture which makes you understand. So you can see this picture first. This picture you see, this is exactly your geosynchronous. So what is happening? My satellite is there. It is having a focus. Okay, it has this kind of focus. It's concentrating on this part. So now what happens? My Earth's rotation and my satellite rotation are synced together. So wherever it moves like this. Right, so the same part of exactly that portion will be covering at different time scales, right? So that's called as geosynchronous. Now what's happening here is when this geosynchronous is called as geostationary is it's nothing but only at equator portion it just concentrates. Okay, when that satellite is fixed only to cover the part at the equator without any inclination, exactly it will be in the plane of equator, then you call it as a geostationary. Okay, so generally if you see geosynchronous for your GPS, you know the global positioning system, how actually your location, you know someone's location, if they give you a tracking, you can track them. All these things, when how are they possible is nothing but your geosynchronous satellites. It requires some 16 satellites coming together at one giving a location. They get synced at one point, then that location is exactly your GPS location. So geosynchronous, the application of geosynchronous is nothing but you can see they are used for weather events. Okay, whether how actually the weather is getting recorded, the kind of television communication, all these things comes under the application of geosynchronous. Okay, coming to the polar one, you can see this polar is nothing but exactly if the synchronization happens with respect to the rotation of the sun, you call it as sun synchronous. Okay, so the kind of photography and mapping, these satellites are generally used. Okay, so I wanted to show you a picture which exactly makes you understand about this. This is exactly your the difference between your geosynchronous and geostationary. Both are actually called as geosynchronous only, but what is the difference is you can see this is the satellite part. Okay, this is the satellite which is getting just orbiting like this. So you can see this is exactly inclined with the equator. You have an inclination of this orbital plane. It is inclined at an angle with the equator. But what is happening to the geostationary? Exactly in the plane of equator only it just moves. Which means that only in that portion it just covers around that equator. It's stationary. Okay, stationary along that plane. Okay, which is synchronized. It's synchronized along with the rotation of the earth and it's an inclination with the equator. Okay, so that's only the main difference. So let's go back and see the content part. So you can see three kinds of satellite orbits which depends upon its position relative to the surface of the earth. They are, first let's see geosynchronous and then we'll move on to the geostationary. Geosynchronous orbit is an orbit around the earth of the satellite with an orbital period that matches with the earth's rotation. So how much rotation the earth is making, obviously your satellites are also synchronized to such rotation. And how much of its rotation on its axis, which takes around one sidereal day, about 23 hours, 56 minutes and 4 seconds. So geosynchronous satellites are often used to monitor weather events or transmit television and communication signals. So that is the application. And if you see the kind of height or the elevation at which altitude at which your satellite is launched is, it's approximately 35,790 kilometers. If you see the geosynchronous or geosatellites, there will be at that elevation. I cannot say elevation, it will be at that altitude. Okay, so it flies, the satellite is launched till that altitude. And how we make that calculation is simply the normal calculation what we do, finding the radius of that. There are two masses now, right, the satellite and your earth. And now you can calculate that, you can use that root over 4 gn by r square formula, whatever we have, that you can make use of that. Okay, a geostationary or a geosynchronous orbit stays in the same spot relative to the Earth. It flies at an altitude of 35,790 kilometers, orbiting with the planet in the same direction. So you should understand that how the Earth rotates, the satellite also rotates. Okay, and at that altitude, it is getting launched. Now let's see what is this polar orbit or sun synchronous. Anything is the same. There are two names for that. Satellites on polar orbit circle the planet on or near the polar inclination, maintaining an altitude of 700 kilometers. So at the altitude of 700 kilometers, we launch these, and it is actually synced to the solar time. These satellites pass over the equator at the same solar time every single day, which allows you to connect the data consistently. Okay, orbiting satellites are generally used for photography and mapping. Okay, so now let's move on and understand how many satellites are there. Okay, what are those different characteristic features? We will not going to see all the satellites, but few of the satellites we will be discussing. Now you can see the other day also I was talking to you about passive and active, right? Source of energy. The solar energy from where it is coming, it's treated as passive source of energy. Why it is passive source of energy? Because it's available for some time scale, right? So when the sunrise happens till the sunset, this energy is available. When you talk about the other source of energy, which is active source of energy. What is active source of energy? You can make use of an artificial energy, right, at any time scale whenever you require, right, and you can make the kind of radiation to fall onto the target, collect the the reflection, and then it is captured by the satellites, right? So that's called as active remote sensing, where you use the natural source of energy, which is the solar energy, for some time scale. You call it as passive remote sensing. Okay, so using passive source, passive remote sensing; using an active source, active remote sensing. So that's it. Okay, so you can see various Earth observation satellites which uses the passive source of energy, which is your solar energy. As there are so many satellites here, you can see AVHRR, Landsat. I have shown you Landsat. It has 9 kinds of different satellites in that. Spot, IRS, Cartosat, ICNOS, CWIFS, GeoES, Meteosat, Terra, EOS satellite. There are so many kinds of, in Terra EOS also there are so many kinds of other satellites being launched. Okay, next to that, if you see active remote sensing, so nowadays if you see in the past upcoming 10 years or so, last 10 years, if you see, this kind of active remote sensing has been increased actually. Okay, you can see the other active remote sensings are ESA satellites, okay, NVSat, Sentinel, Canada Radarsat, Indian is RESAT, Japanese is ALOS. These are different active remote sensing. So as of our content is concerned, we are actually interested in knowing about passive remote sensing only, because that's the technology which we are using currently in India. So we are actually concentrating on passive remote sensing. If you wanted to see about the active, there is an advanced course on active remote sensing also. You can refer the kind of NPTEL courses where you will find so much of information on active remote sensing, because it becomes an advanced kind of thing to you. Okay, so about for all of these passive remote sensing, we will see some of them. Okay, the first kind of this slide I have already shown you. Okay, earlier also, Landsat. So Landsat is basically, if you understand, this is a kind of, it's not a kind of Indian satellite. Okay, it's an American satellite basically. Okay, and it has so many versions in it, so many different satellites in it. Landsat 1 starting from 1972 to Landsat 9, which is the recent one, which is the 2021. Okay, and Landsat 8 February 2013 is the latest one, where you can get so much of freely available data is there. Okay, all are free. You can download all of the Landsat starting from 1972 to 2019 till date. Each data is there freely available. Okay, and the other day when I was showing you this slide also, we were talking about the overlap period, right? What are the different changes have been made from one year to the other year? Okay, you will understand when I will show you the sensors, what are the kinds of their bands which are used, then you will understand. Okay, so let's see them. So Landsat 1, we will just talk about this little, what are the sensors which are present, and then we will talk about the last Landsat, which is your Landsat 8. Okay, Landsat 1 is basically Landsat 1 started in July 23rd, 1972, and till 1978 it was being used. Okay, what type of sensors it has? So earlier also when I was talking to you of the remote sensing technology, how it got developed, earlier I said they were used to use cameras, which actually has some lens in it, right? But gradually when you see the kind of satellite has come into picture, what is the technology being used there is they use an optical sensor, okay? Or next to that sensor, what has come is your scanner, okay? So basically, what is that satellite? What has or what are there in that satellite are nothing but you have sensors in that, you have scanners in that. Okay, so the Landsat has two kinds of sensors in that. One sensor is called as RBV, okay, and the other one is called as Multi-Spectral Scanner. So what does this do is, you can see RBV. RBV is a type of optical sensor which has a resolution of 80-meter ground resolution. So I said you what is meant by ground resolution or spatial resolution. The other day we were talking about spatial resolution. Spatial resolution is nothing but the resolution at which two objects will be clearly visible. Okay, if I say 80-meter resolution, which means that all the objects which are having a distance between them greater than 80 meters will be clearly visible on my satellite image. Okay, less than 80 meters, both of them show as a single object. Okay, so that's meant by 80-meter resolution. That is your spatial resolution. What is the spectral resolution of this RBV sensor is? Spectral resolution is it has 3 bands in it. Okay, so what is this 3 bands? Remember our remember our electromagnetic spectrum? We talked about visible light, we talked about infrared. Okay, so here if you see in your RBV sensor, what happens is you have 3 bands in it. What are those 3 bands? What is the range? 475 to 575 nanometer, which is nothing but 0.447 to 0.57 micrometer, whatever we have seen earlier in that notation. Okay, next to that you have band 2, which is nothing but 0.58 to 0.68, and band 3 is visible red to near infrared, which is nothing but 0.69 to 0.83. So which all portions we are actually covering? We are covering some part of blue-green, we are covering some part of orange-red, and we are covering some part of red and infrared. So in these three portions, wherever the wavelengths are available, when the targets get interacted with these wavelengths, the reflection is being captured at these wavelengths. Okay, so let's say RGB and the infrared is falling onto the target like this. What happens? The sensor which is sitting RBV, what it does is when the reflection happens like this, in these certain wavelengths, it will capture all the reflection corresponding to 0.47 to 0.57, 0.58 to 0.68, 0.69 to 0.3, okay, 0.83. Next coming your multispectral scanner. So only this sensor RBV has 3 bands in it, okay. It can only capture in those wavelengths only. Next coming your multispectral scanner, again it has a resolution of 80-meter. 80-meter ground resolution. Already I said it's a spatial resolution. What about the spectral resolution? Again, it has 4 bands in it. What are those 4 bands? You can see band 4 is visible green. Directly green, 0.5 meters to 0.6 micrometers. Directly red, 0.6 to 0.7. Near infrared, 0.7 to 0.8. Near infrared, another band, 0.8 to 1.1. So you can see the different wavelength ranges. Earlier 3 bands has different range, these 4 bands has different range, right? And now what is happening? All these 7 bands are designed for this satellite, and when this satellite goes there, whatever the reflection is coming from the ground in these respective wavelengths is being captured. And after getting captured, what it will do? It will translate that, or it will convert that reflection into a readable format, which we will be able to understand. Okay, so you can see 6 detectors for each spectral band provide 6 scan lines on each active scan. Okay, you will not understand this part of 6 detectors, which I will be talking in the next coming 2 classes. about the kinds of scanners. When I talk, no, you will understand what is a scan line, what is a scanner, what is a detector, the entire process, how actually the capturing will happen. No, that process we will talk a little later in the next class. Then you will understand the sentence. Okay. So ground sampling interval is nothing but the pixel size is 57 by 79, which is nothing but just now I said 80-meter resolution. So the kind of capturing which happens, no, it is at the range of 80 by 80, which is exactly, if you talk, it is 59 by 57 by 80 meters, which we will see why it is less than 80 by 80. Okay. So that's about your two sensors within Landsat 1. So now move on to the next latest one, which is Landsat 8. What is the difference between your Landsat 8, which is the latest one, and Landsat 1, which is the oldest 1972 one? Okay. So same thing, Landsat 8 is actually called as Landsat 8 OLI. Why it's called as OLI is nothing but the sensor which we use here is OLI sensor. OLI is nothing but operational land imager. Okay, it is also a kind of scanner, okay, which actually has 1 to 7 bands multispectral, okay, and which is at a resolution of 80 meters, and the other band, ninth band, is 30 meters, and there is another band which is of 15-meter resolution. So what exactly it says is, from 1 to 7 bands, they are designed for 80-meter resolution, which means that two objects which are away at a distance of 80 meter will be clearly seen. Okay. What does ninth band do? Ninth band covers the objects which are there at 30-meter resolution. 30 meters means whatever are at a distance greater than 30 are clearly seen. Okay. And yet there is another band which is covering at a resolution of 15 meters. Okay. So, and after that, we have seen 1 to 7, 8, 9 is over. The other two bands, which is 10 to 11, which collects in TIRS. Remember TIRS, thermal infrared. The next to the reflected infrared, which is from 3 to 1000 micrometer, whatever we have seen, it collects at 100 meters, but resampled to 30 meters to match the OLI spectral bands, which is nothing but it collects at the resolution of 100 meters, but a resampling has been done and it is used at 30 meters. Okay. So I'll show you a picture where you can understand how the technology is getting increased. Okay. So you can see here there is actually a picture or a comparison which has been shown between your Landsat 7 and 8. Okay. So just observe this. On the x-axis it's the wavelength which we are able to see, and on the y-axis it's nothing but the kind of what do you say, the atmospheric transmission is nothing but where you are able to see a kind of black shade or a gray shade. It's nothing but high transmission has been happened there. Okay, 100-meter transmission, 100% transmission. 100-meter transmission is a white color. Okay, wherever we are able to see, it's nothing but the atmospheric window. Okay, what is happening in the 7 is, 7 has how many bands? 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, and 8. So if you see the kind of wavelength ranges, how your wavelengths are designed, one is nothing but your blue is there. Okay, blue, green, red are there, and after that a small portion of infrared. Next coming, you have entered into middle infrared. Next, thermal infrared has come into picture for 7 and 6. And where is your 8? 8 is a very big band where you can see it's covering moreover from green to infrared, right? So that's the information about your, the Landsat 7. But what's the difference with the other one? You can see the Landsat 8, what it is showing, 1 is here, 2 is here, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So what has happened, if you just observe the difference, and a small difference which a layman can also understand is, when compared to 7 and 8, what is happening? The narrowness in the bands have come into picture. Narrowness in the band. Narrowness in the band is nothing but narrowness in the wavelength ranges, right? So because if some specific objects are wanted to be captured, where I know that vegetation only responds to green and infrared wavelength, so that I will choose only green small part and infrared small part, rather than keeping the entire range. If I even cover also, my vegetation don't respond in the rest of the what do you say, rest of the red and blue, I will not see any kind of reflection coming into picture. So by narrowing my reflection, my wavelength range, what is happening? Your information getting collected is getting improved. So band or satellite by satellite, version by version, if you see what's the improvement is, narrowness in the bands have come into picture. And now if you see the ninth one, very narrow, you have some kinds of 20 bands in it. Okay, so in the next slide, I will show you a chart where you will easily understand what's the difference. So Landsat 7 actually has 8 bands in it. What are those? Blue, green, red, near infrared, shortwave infrared, thermal infrared, shortwave infrared, another one, and there is a panchromatic which actually covers from visible region, visible to infrared. Okay, and when it is coming to Landsat 8, what has happened? You can see there's a violet band here, next to that blue, next green. If you see the green ranges also, here we are covering from point, here we are covering from 0.5 to 0.6. Okay, here what did we make? We make a very narrowness, 0.533 to 0.59. Okay, and here also you see red band 0.63 to 0.69 it is covered. Here what has happened? He has narrowed it 0.636 to 0.67. So narrowness, when it is coming into picture, rather than getting the information where exactly we require, we are maintaining that part. Okay, and next one, if you see near infrared, next is shortwave infrared, next thermal infrared, and next there is a panchromatic, very big band from 0.5 to 0.67. So these are the different band informations which are actually used in this Landsat 7 and Landsat 8. Okay.
So we will stop our discussion here. We'll see you again in the next lecture. Thank you for your attention.